Hi everybody, welcome to the lesson on one-sample t-tests. So the one-sample t-test is used when you want to compare the population mean to a constant. Now that was the same thing that we were testing when we looked at the one-sample z-test last week. The difference between the z-test and the t-test is that the z-test assumed that sigma, the population standard deviation, was known. In real life, we really never know sigma. If we knew the population standard deviation, we'd know the population mean and we wouldn't have to run a hypothesis test. So if somebody in real life wants to compare mu to a constant, this is the test they run. Now it does require a different assumption though. It requires that the data follow approximately a normal distribution. So you know how to do that. We've done that before. You just evaluate normality using the Kolmogorov-Smirnov test, the normal probability plot, skewness and kurtosis, and also look at the histogram and box plot for kind of confirmation of what you're seeing in the other places. The good news is, if your data isn't too far off normality, you can still run this t-test. We have this statement we use that says for large sample sizes, the t-test is robust against mild departures from normality. This word robust is a formal statistical word, and I was trying to underline that and not work through it. This is a formal statistical word that means the test still performs well when there are mild departures from normality. So if there is actually a difference, it catches it without catching differences that aren't there. So that statement is our friend that we'll use. So basically what you're going to do before you run the test, you're going to evaluate normality like we said. If the data follows approximately a normal distribution, and I phrased this in a funny way on purpose because I want to emphasize we cannot say for certain that the data follows a normal distribution, no matter what we do, because we don't have the entire population. But we can say that it appears the data follows a normal distribution, or the data does not depart significantly from normality, something along those lines. There are variations you can say. You just can't say conclusively, this data follows a normal distribution. Don't do that, I'll count off. But if you have one that's approximately normal, then just say so in the write-up. You're going to state your Kolmogorov-Smirnov test p-value, state your skewness and kurtosis, and keep going. If the data is non-normal according to those metrics, but it's not too far off, you can still run the test as long as you have a large sample size. And you can just put this statement in there, that the t-test is robust against mild departures from normality as long as the sample size is large. Okay, that's all you need. The question you may be asking is, well, how non-normal is non-normal? And the reality is that is a judgment call. That's a judgment call. I would say the larger the sample size, the more tolerant I would be of non-normality. If the data is badly non-normal and you don't have a large sample size, don't do the test. Instead, you would do one of the non-parametric alternatives. Non-parametric, those are a set of hypothesis tests that we'll learn about later on in the course that don't rely on this assumption of normality. So we'll do an example where we do all of this. So let's talk about our hypotheses. We've got the same set of hypotheses as before. We've got our null hypothesis is always that mu equals some hypothesized value. And our alternative hypothesis could be that mu is less than our hypothesized value, or it could be greater than, or it could be not equal to. And just like before, the not equal to, this is our two-tailed alternative hypothesis. Whereas these other two, if we have either of those are one-tailed. Okay? And that's going to be important to us. I've got our formulas here for the test statistic and the p-values. I put them here just so you can see how similar the t and the z are. The only thing different between the t and the z is in the test statistic is that in the z formula we're using sigma instead of s. And then in the p-values we're just using a wider distribution. But you don't have to use those formulas for anything. We're going to get those from SPSS. Another thing I want to point out to you here is that if you've got a two-tailed p-value and you want to find the one-tailed p-value from it, the two-tailed p-value is twice the one-tailed p-value. So to convert a two-tailed p-value to a one-tailed p-value, you really just have to divide by 2. Okay, and I tell you that because in SPSS, they're going to give you the two-tailed p-value on all of these. They're not going to give you the one-tailed. And if you want to make it one-tailed, you really just have to divide the p-value by 2. All right, so let's do an example. I want to use the attention span data set to test whether children watch less than 10 hours of TV on average per week. So I've already got that pulled up over here in the virtual desktop. Over here, and it's in Canvas, it's attspan.sav. It's like over there. So the first thing we need to do is check our normality assumption. Oh, let me tell you a little bit about this data set first. This data set gives you, I think it's got 40 observations. And this is adolescent students, like middle school age students, and it's just some basic information about them and some things that might be related to their attention spans. And you can see what these values are here. So in this example, we're looking at TV, whether the mean amount of time they watch TV exceeds 10 hours per week. But we first have to check for normality. So let's go to Analyze Descriptive Statistics, just like we've done before. Explore, and we're going to take that variable, move it over to the dependent list, and I'm going to turn off the stem and leaf. I'm going to turn on the histogram, and I'm going to run the normality plots with tests. All right, so what we're looking at right now is the normality measures. So we've got a skewness of 0.725. That's within the normal range. Kurtosis is a little bit high, but let's see what everything else says. The p-value on the Kolmogorov-Smirnov test is 0.2, so that's a good sign. Histogram looks pretty good. Looks fairly normal. This looks fairly normal too, except for this one observation. Looks like it might be an outlier. And that's what we see on the box plot as well. We have one outlier, somebody who says they watch 24 hours of TV per day. Is that right? Was that per day or was that per week? Let me check. Okay, per week. Okay. That's still a lot, but at least it's technically possible. Okay, so with all of that, it looks like it's close enough to normal. I would call it normal. Especially, I think the thing that carries the most weight is the Kolmogorov-Smirnov test. All right, so now if we run the hypothesis test, that is under analyze, analyze, compare means, one sample t-test. Okay? And I'm going to write this in over here because I didn't have it written down. So analyze, one sample t-test. Actually, it was analyze, compare means. One sample t-test. And you're going to move your variable over. So our variable is TV. And don't forget to enter the test value. The test value is the hypothesized value. Okay, so ours is 10 hours per week. And we'll click OK. And I'm going to write this over here as well. Enter the hypothesized value as the test value. All right, so now what are we looking for? Well, they gave us the sample size, the mean, and the standard deviation. That was good, although we already had that. This tells us our test statistic and our p-value. And this is the p-value for the two-tailed test. So if we wanted to test for mu not equal to 10, this would be our p-value. Okay? So our hypotheses are mu equals 10 versus mu less than 10, because we want to know, are we watching less than 10 hours a week on average? Our test statistic, which again came from over here, was negative 1.027. And our p-value for the two-tailed test would have been 0.311. But we want the one-tailed test because they asked us here, is it less than? Okay, so that's going to be one-tailed. So we take our our sig two-tailed divided by 2. So that's our p-value. And remember, we're always rejecting H0 for small p-values, less than 0.05. So this tells us that we will fail to reject H0 and that there is not sufficient evidence to conclude that the population mean is less than 10 hours of TV on average per week. All right? So that's our hypothesis test right there. I need to talk to you a little bit about effect size, because from here on out, just about every hypothesis test we're going to do is going to have some measure of effect size. Effect size is a response to two primary criticisms of hypothesis testing. The first criticism is that hypothesis testing just gives you a yes or no answer. It's all or nothing. Can I conclude this or can I not? There's no subtlety. There's also no further information. And I guess that's getting into the second part here, which is it doesn't really talk about how big the difference is if there's a difference. It just says, can I conclude there's a difference or not? And there's one more criticism that I'll say, and that's that it's highly dependent on the sample size. It doesn't matter how small of a difference you have. If you have a large enough sample size, it's going to be statistically significant. So if I were running this last hypothesis test, say the sample mean was 9.9999999 hours of TV on average per week. That's not very much below 10 hours. It's not in any kind of meaningful way. It's not. But if I took a sample size of, I don't know, 1 million, that would probably end up being statistically significant. So effect size takes the sample size out of the equation, and it gives a little more granularity to your answer. So a lot of these sample sizes that we're going to see at the beginning were devised by this guy named Cohen. I think his first name was Jacob, but I'm not sure. So this is a simple thing to calculate. This is just you take your sample mean, subtract your hypothesized value, take the absolute value, and divide by the sample standard deviation. For our attention span data, Cohen's D is calculated as the absolute value of, it was 9.25 minus our hypothesized value, which was 10, and then we divide by the standard deviation, which is 4.619. And if we do 9.25 minus 10, we'll take the absolute value of that, make it positive, and we'll divide by 4.619, and this is 0.1624. So we'll just call that 0.162. Okay? So the interpretation here, and Cohen said he really didn't even want to give guidelines. Because one of the reasons he devised this was because people just ran hypothesis testing and they would just, plug in the numbers and say, oh, statistically significant, here we go, without really putting any thought into it. And so if all you do is get this value and go, okay, I'm going to compare it to one of these, 0.162, that's weak, boom, then you're not really doing anything. You're not making an improvement. So keep in mind that anytime you run a hypothesis test and do an effect size, your interpretation should be compared not so much to these guidelines as to effect sizes of similar research. So you should look in the field, do your lit review, find out what other similar studies have found for their effect sizes, and really compare to them, not so much to these rough guidelines. Having said that, this one is a small effect size. Okay. So this tells us, the way I think of effect size is it's kind of like, with a hypothesis test, it's kind of like a yes and or a yes but. Yes, I can conclude that the population mean is less than 10 hours per week, but it's not by much, which is kind of what we have here. So based on the hypothesis test, we found that yeah, in the population, we're able to say that mu is less than 10. But according to this, it's not by much. On the other hand, if we had gotten, a Cohen's d of 1.162, we could have said, yes, we can say that the population mean is less than 10 hours per week. And it looks like it's below by a whole lot. So that's what that's good for. By the way, I don't think it makes sense to talk about the effect size when you don't have a statistically significant test in the first place. So if you haven't been able to conclude that you have an effect, there's not much sense talking about the size of the effect that you haven't found. So I don't even talk about the effect size unless I have a statistically significant test. So these are our steps. We've gone through, we've checked our assumptions, we've set up our hypotheses, we got the test statistic and p-value from SPSS. We know our rejection rule is reject H0 if p-value is less than 0.05. We've stated the conclusion, which is that we fail to reject H0. In this case, we cannot conclude that, oh wait, what did we do with this one? Yeah, okay. We failed to reject H0. There is not sufficient evidence to conclude children watch less than 10 hours of TV on average per week. And just to show you about effect size, we calculated that. But in general, if you don't have a statistically significant test, you don't have to do that. Sometimes there will be a seventh step here, which is to run post hoc tests, but we haven't seen any tests yet that have those. Now, at the end, you're going to have to do a write-up of your test. And these are the elements that you need to include. You need to start with just a quick one-sentence summary of what we did. What were we trying to test and what test did we use to do it? Evaluate your assumptions. You're going to state any relevant descriptive statistics. And then you're going to tell what was the result of the hypothesis test. And if you had a statistically significant test, you're going to tell the effect size. Okay? So I wrote up a sample write-up just to show you what this looks like. I don't want you to write this down word for word because I don't want you to use it word for word and just change a couple of numbers here and there. I wrote this so that you could get an idea of what this might look like. So a brief summary of what test we ran. We ran a one-sample t-test to determine whether children watch less than 10 hours of TV on average per week. So that's that first part. Evaluate the assumption. The assumption of normality appears to be met. Again, not stating it conclusively. Stated the skewness and kurtosis and the Kolmogorov-Smirnov p-value. Okay, it is common to put parentheses around some of these numbers like this. So skewness, kurtosis, and this is the p-value. These are supporting statistics for the statement we just made. So that's the assumption statement. State relevant descriptive statistics. The children in the sample watched a mean of 9.25 hours per week with a standard deviation of 4.619. I might specify the 40 children in the sample. So that's our descriptive statistics. And then the result of the hypothesis test is at the 0.05 level, the test was not statistically significant. And you state your test statistic and you state your p-value. I didn't say anything about the effect size because we did not have a statistically significant test. All right, so that's it for this lesson. Stay tuned for the 2-sample test for T.